Hi, my name is Matteo Destro, and today I'm going to present CycleCL, a novel self-supervised learning method for periodic videos. This work was done at Sirion in collaboration with Michael Gygli. So repetitive processes and actions are very common in multiple domains. Here we see some examples of these repetitive processes, and they can be found in, for instance, human exercises, production processes in manufacturing, satellite imagery for seasonal changes, or medical MRI for biological processes. So having feature representations that capture the key aspects of data periodicity can have a large range of useful applications. In this paper, we addressed the problem of learning useful feature representations from repetitive videos with the final goal of performing anomaly detection. These repetitive processes usually present constant repetitions at regular intervals, and then we have some occasional deviations that break the cycles, and we can see below. The anomaly detection task consists on detecting these visual deviations. So to achieve this task, we first need to learn feature representations with particular properties, and we propose to do that by exploiting the repetitive nature of the data using contrastive learning. So in contrastive learning, the model is trained by first selecting a set of positive samples that have some common properties with the anchor, and therefore they should be close in the embedding space, and then selecting a set of negatives samples that instead should be mapped to a further region of the space because they don't have these common properties. Once these two sets are defined, the loss is minimized so that the positive representations are pulled towards the anchor, as you can see here in this image, while the negatives are pushed away. So many contrastive methods like CycleCL do not account for the particular properties of this type of videos. For instance, in CycleCL, all the other frames are selected as negatives. But given the limited variability of the visual signal in repetitive videos, these can lead to selecting as negatives frames which are very similar to the anchor. So we can see here an example, for instance. So the two frames are like semantically very similar. And if they will be selected as negatives, then they will be pushed apart in the embedding space, and this will affect the training process. Moreover, repetitions provide a source of real-world augmentations, so a method able to take into account this kind of properties of the data could benefit from it. So to be useful for downstream task, the learner presentation should be sensitive to the progression of the cycle, so that they can focus only on the relevant semantic differences between the stages of a single repetition. So we can see here an example where we have a machine producing bottles. Every new repetition starts with a particular configuration that we can see in the anchor frame. And if we see in the second repetition with the frames marked in green, we can see that the visual content is basically the same. At the same time, the representations that we want to learn should be invariant across repetitions. So here we see these negatives frames marked in red, which are like the stages after the beginning of the production process. And we can see that the bottles are pushed away and the visual content is significantly different. So to learn features with these properties, we design a new sampling method for contrastive learning that tries to sample negatives from different stages of the cycle, as we see here in this image, marked in red. So the model is able to focus only on the semantically significant part. And the model can learn to be sensitive to the progression. And at the same time, we want to sample a set of positives from frames whenever the same step is repeated. So the representations, for example, for these frames marked in green should be very, very similar to the ones of the anchor. For the selecting this set of positive frames, we use the similarity between the frames in the embedding space. And the core idea is that similar inputs should produce similar embeddings. So selecting frames with a high similarity with the anchor should produce a set of good positive samples. This set of good positive samples is composed of frames that most likely belong to a repetition of the same step of the anchor. So using a similarity to do that provides a simple way to achieve better than random accuracy in the selection. We first compute the temporal self-similarity matrix using the pairwise distances between frames in a single video clip. We see an example here in this image on the right. And then we use the similarity as a threshold to select the set of positive and negative frames for each anchor. We obtain these embeddings by using an encoder composed by a backbone pre-trained on ImageNet, followed by a projection head that uses 3D convolutions to add temporal context. So the result is an embedding vector for each frame. We then perform the selection mechanism, as I already explained, based on the mean of the similarities, and we obtain a set of positive and negatives, and then we can finally train the model using triplet loss, and we iterate between sampling and optimization until convergence. So if we plot the distances of a frame with respect to its successor, in the beginning, as we show here in the first plot, we cannot see any kind of repetitive behavior. So the representations are kind of suboptimal and don't have the properties that we actually want. Despite this noise, there is still sufficient signal about what could be a likely positive and negative, so that our selection mechanism is still able to sample good initial triplets. So in fact, while we iterate between sampling and optimization, the selection becomes more and more precise, and we get more and more relevant positives and negatives during the training. And if you plot the same distances after just a few epochs, we can see that they are much more consistent, and in this case, we can clearly see the repetitions. So this is a good indication that the model has learned good feature representations. So for instance, we can see that the distances drop to 0 whenever a new repetition begins, and instead are much higher during the progression of the cycle. We evaluate our method on 4 different datasets, one collected internally depicting production lines in manufacturing. And then we also evaluate on a different domain, so on 3 public datasets representing human actions. So here the diversity is much higher and interruptions are more common. And we show that our method is able to perform well on both domains. So here we have a first analysis of the features. If we plot the temporal self-similarity metrics, in a normal video, we see all these constant patterns, and each diagonal line represents a new repetition. While if we do the same with an anomalous videos, we see these kind of interruptions are clearly visible in these boxes pattern in the similarity. But if we do the same for embeddings extracted from ImageNet model, we don't see this kind of pattern. Instead, there is only a strong similarity between a frame and itself. So for a more quantitative analysis, we first analyze the goodness of the learned features by trying to compute how well the embeddings of normal and anomalous samples are separated in the embedding space. We perform weighted K9 classification on the embedding extracted from each frame, and we try to classify whether a frame belongs to a repetition or if it belongs to an interruption event. We compare against other methods for self-supervised learning, and we can see that we are able to obtain good results in all the 4 datasets, while CycleCL has the problems that we discussed before and actually hurts the performances with respect to just a model pre-trained on ImageNet. You can find more experiments in the paper. We then perform another evaluation based on anomaly detection task. And in this case, we apply simple density estimation methods on top of the learned features, and we try to detect the interruptions. So the difference between this and the previous task is that in this case, we don't use labels at all, and we classify a frame based on its distance between its neighbors. Here we compare using the raw embeddings with an intermediate representations that encode the cyclical patterns of the video. With this approach, using this kind of representation, we achieve an F1 score of 52 using just a simple K9 classifier on the industrial dataset. This is a strong result for a totally unsupervised method, given that in this particular dataset, interruptions and anomalies are very, very rare. So to conclude, we propose CycleCL, a cycle-contrastive learning method to exploit repetitions in videos to learn useful representation. It's based on a novel strategy that uses feature similarity to select a set of positive and negatives to use with contrastive learning. And our method is able to outperform other approaches for self-supervised learning on 4 different datasets. So we show that it's affecting on different domains on both static and dynamic camera scenes. So this is all, and thanks for your attention.